In this example, I'll do Coletta 713, which discusses airbags. The problem starts by giving us a little background that airbags are used to decelerate occupants slowly when a car is suddenly decelerated during a crash. And then the task we're given in Part A is to compute the work done by the decelerating force acting on a 55.0 kilogram driver if the car is brought to rest from an initial speed of 20.0 meters per second. Good, so this is task A. There's also B, and we'll get to that later. So in a work and energy problem, which this one is, we can start by with our analysis by telling ourselves the story of what's going. Okay, there's a person, they're moving in the car at 20 meters per second. Suddenly, the car stops abruptly, and the person goes from 20 meters per second to rest. We know how heavy they are. Because we know their velocities and their mass, we could probably get their kinetic energy. And there is this implicit information that we end at rest, so we end with zero velocity. All right, the next step is to draw pictures, identify forces, and figure out if the forces are conservative or non-conservative. Lists are known and goals. So that's pretty much all the analysis in one step in my work and energy problem solving strategy sheet. So go ahead and see if you can do that step, kind of the analysis step. All right, here's my analysis so far. So I drew a little picture. This circle is the person. And they start by going 20 meters per second along with the car. And at the end, they're going 0 meters per second. We know their mass. And then initially, this looks like it could be a kinematics problem, right? If this was constant acceleration, then we could probably figure out from initial and final velocity, we don't have time. So maybe it's not. But the fact that mass is in here is also a good indication that it's not kinematics. Giving us the mass means we have now enough information to get kinetic energy, and it's a hint that it might be a work energy problem. I've also drawn a free body diagram of the person. As always, they have their mass and normal force, but then they have this other force slowing them down, the decelerating force that the question's asking about, and that would be the force of the airbag. Okay, now let's think about if there's any other knowns, and I can write down my goal. Okay, I didn't find any other knowns, although in a careful review I found I wrote down the wrong mass initially. And then I wrote my goal is the work done by this force of the airbag, the one here in this drawing. And we know that the person is only moving in the x direction, only along this direction. So these forces, which are perpendicular, don't do any work on the person. Only this force airbag of the airbag does negative work because the force is in this direction and the motion is in this direction. So when force and motion are opposite directions, we get a negative work. So I can rewrite this work done by the airbag as the net work or the work done by all the forces because the airbag is the only force that does work on the person. So my goal then is the net work done on the person. All right, so now I want to get to my planning step and figure out which of our work and energy equations would be the right one to use. See if you can do this on your own. All right, here's what I did to get to this plan. I first considered if I could directly calculate work, and to do that, I would need to know the forces and the distances. Since I don't know the distance here, that's not going to be a good option. Then I went to step 4 of the problem-solving strategies and tried to think, are all the forces conservative? Well, that would mean just gravity and spring forces acting, and here I have the force of the airbag. So that's not a conservative force, and so I can't use the equations, the conservation of mechanical energy. That means I need to get down to step 5 and choose which of those two equations to use. Either one of them will work, but since the height's not changing, I decided that this would be the easier equation that tells us that the net work done on an object is equal to its change in kinetic energy. And we've already discussed how we have the information to find the change in kinetic energy. That would be the final minus the initial kinetic energy. And here, in case you've forgotten it, is the kinetic energy equation. The kinetic energy is a half mv squared, right? We have m, we have v, initial and final, and so we can go ahead and find those kinetic energies. Go ahead and see if you can execute this plan now. I started this by figuring out my initial and final kinetic energy. Final kinetic energy is easy because it's a half mv squared and our final velocity is 0, so that's 0. Then our initial kinetic energy comes from our start time. It's a half mv naught squared, our initial velocity squared. I plugged in those numbers and I got 11,000, and I wanted to think a little about the units. They're kilograms meters squared per second, which is, if I separate the meters squared into a meters times a meters, I get a kilogram meter per second squared. Oh, I'm missing a second squared. Look, the second was squared. This here, kilogram meter per second squared, we'll recognize as a Newton, which means overall our units are newtons times meters. The Newton meter is a measure of energy. It's called the joule. All right, so far we figured out that our final kinetic energy is 0, our initial kinetic energy is 11,000 joules. So now we want to go on to find our change in kinetic energy, set it equal to our net work. All right, so there I did that step, and it was pretty easy since we only had this 11,000 here. But notice, because of the way that the change works, final minus initial, it turns out that we subtract this, and we add up, we have a negative change in kinetic energy, right? We end up with less kinetic energy than we started with, which means that our net work done is negative. So this will be a great place to do a little monitoring and see if that makes sense. As we said before, the force of the airbag, which is providing our net work, is in the opposite of the direction of motion here. We're going from the right, we're moving to the right, and this is slowing us down, decelerating us. So the fact that it's opposite the direction of motion means we expect that the work that it does is negative, because F is negative and delta X is positive. So here we go. That seems to make sense. Which means we should probably move on to part B. So I'm just going to copy this information over here so we have it for part B and move on to part B. All right, part B of this question is find the minimum thickness of the airbag if the average decelerating force is not to exceed 8,900 newtons and the center of the car moves forward 0.800 meters during impact. Okay, so now we have a new problem where we still have all this information from before, but we have some new things to add. So I'm going to add these to my picture, and now that we have this, I'm actually going to draw a little bit of more detailed picture. And it's just part B that makes this a starred problem because it's just got one little wrinkle that makes it difficult. So see if you can think of that wrinkle and add this information in. All right, this is the drawing I made of now I have to think about the person moving separately from the car, right? Because what I know is that the car goes 0.800 meters, and that's a picture of the car moving here. But here's the person inside, and what I know about an airbag is that what it does is it allows the person to continue moving forward in a controlled way after the car's done moving, right? And it's the airbag that lets them move from where they were to a little bit farther forward in a nice cushioned way and not keep going forward into the windshield, right? So this little extra bit that the person moves is the thickness of the airbag, where they move from wherever they were in relative to the car to a little bit farther forward. So what that means is the total distance that the person moves is the distance that the car moved plus the thickness of the airbag, right? This delta X, the total distance the person moved. All right, and then I also know a new thing, which is I now know the force of the airbag has to be less than a certain amount. And so I could probably consider this force to be the force of the airbag and just make sure it never gets bigger than that. All right, so I'm going to consider this to be another energy problem because now I know a force and a distance, which is looking really good for just the easiest kind of energy calculation. So let's see if you can use that information to make a plan. All right, here's my plan. I want to find delta X, this total distance that the person moves, and then once I have delta X, I know I can use that to get D, the thickness of the airbag, because this total delta X is just the part the car moves plus D, right? So delta X is 0.0800 meters plus D, so if I know delta X, I can easily do some algebra to solve for D. Then, as I go through my list, I'm first going to consider if I can directly use the Fx delta X equals W net, and that only works if it's actually the sum of all the forces on the left-hand side. But that doesn't matter too much here because we only have one force in X, the airbag force, right? So what we'd have is F times delta X equals W net. To get delta X, we would need to know both of these things. And indeed, we figured out the net work in the first problem, and then we know the maximum that the airbag can be here. And if the airbag's at its maximum, then delta X will be at its minimum for the same work net, right? And we could always have delta X be bigger, and the sum of the forces of X could then be smaller to get the same net work of this minus 11,000 joules. All right, so go ahead and see if you can execute this plan. Really, once you've done the planning, the execution isn't that bad, right? I solved this equation for delta X with a little bit of algebra, plugged in my numbers. I'd had to be a little careful to remember that a joule is actually a Newton meter, and since the denominator is in newtons and the numerator is Newton meters, these two newtons cancel, and we get that the total distance a person goes is 1.236 meters. All right, and up to here, if our goal had been delta X, the total distance that the person goes, this would have been a normal unstarred problem. But now we have this extra step where we had to draw this picture and realize that the thickness of the airbag is the extra little bit that the person goes after the cars stop moving, the 0.800 meters. So now we just need to solve for D, the thickness of the airbag, given that we know this total distance. All right, so here I just did a little algebra with this equation, plugged in the numbers we have, and found that the extra distance the person goes, which must be the thickness of the airbag, is 0.436 meters. Then on my monitoring, I went to check my significant figures and realized this one only has 2. So I better only keep 2 significant figures, and I get 0.44 meters. I want to just stop and make sure that makes sense. So it's about half the distance that the car traveled. So it's not, my drawing up here isn't to scale, but actually that makes sense because this distance that the car went is probably actually a lot smaller compared to the car, right? So it kind of makes sense that if the car stops abruptly, you go about half the distance that the car goes into your airbag. So this would be the thickness of the airbag that would cushion you enough to keep your force relatively small. All right, I think we're done.